In this lecture, I'm going to talk about interior point method. So basically, we use interior point method for both linear and nonlinear convex optimization problems. But our main focus here is on nonlinear convex optimization, because for linear case, we explained that we are going to use simplex as an efficient way. So the goal here is to transform your nonlinear inequality constraints into equality constraints. But how can we do that? Using interior point method. So here is the general idea. Let's say we have minimizing a nonlinear convex function f of x subject to inequality constraint h of x less than or equal to 0. So we are going to define barrier function, and this barrier function is going to help us to consider this constraint in the objective function. So we are going to have minimizing f of x plus the barrier term or the barrier function. Let's call it barrier function of h of x. All right. How do we want to enforce this? The barrier function or the barrier term avoids leaving the feasible region. All right. What does that mean? It means by adding this additional term to the objective function, we make sure it only it penalizes our objective function when h of x is greater than 0. So what's going to be the ideal barrier function? The ideal property of barrier term. So in the ideal scenario, I want to penalize my objective function by infinity if h of x is greater than 0. So if h of x is greater than 0, that means I'm out of the feasible space, right? So I want to penalize my objective function. So I expect the barrier function value to be infinity. And when h of x is less than or equal to 0, I expect my barrier term to be 0 in the ideal scenario. So the function, if I want to just draw the function, it's going to be something like this in the ideal scenario. So this is h of x. If h of x is less than 0, and this is the barrier function, b of h of x. The barrier function value is 0. If h of x is greater than 0, the barrier function is infinity. But as you know, this is not a well-behaving function. So we want to use a continuous function. So we have to define an approximation of the ideal barrier function. So the approximation, we want to choose a function which is twice differentiable. All right, so we define b of x to be -1 over t logarithm of minus h of x. All right, so this is a good approximation of the ideal function that we have. Now we want to see some discussions of the barrier term. So let's write it down here again. -1 over t h of x. So the features, t is a small, So we choose a very small value for t. So this is just a constant coefficient. If t is small, approximation of the barrier term is not the greatest. All right. So we are going to have a large term in our objective function if we choose a small value of t. If t is large, approximation improves. So we have a more ideal barrier function, which is close to what we had here. So this is h of x, this is b of h of x. But the function f of x plus the barrier term is difficult to minimize. So when we want to use Newton method, it's difficult to minimize. And what's the reason? Because the Hessian matrix rapidly approaches the boundaries of our feasible set. So if t is very small, the approximation of the term is not great. So we don't want this scenario. If t is very large, then the approximation increases, but the function f of x plus b of h of x is difficult to minimize. So what we do, we use an iterative process in order to address the trade-off between large and small values of t. We use an iterative process. And increase the value of t at each iteration. So this way we are step by step improving our process, the process of using interior point method until we reach convergence. All right. So another way to deal with the nonlinear inequality constraints is to reformulate the problem and adding a barrier function, but this time we are not going to completely get rid of the inequality constraint. We just transform the inequality constraints, the inequality nonlinear constraint into equality nonlinear constraint. So how does that work? Reformulate the problem. So let's say you have minimizing f of x subject to g of x is 0 and h1 of x less than or equal to 0, h2 of x less than or equal to 0, and h sub p of x less than or equal to 0. So how do we transform this? We have minimizing f of x, so this is similar to before, minus zeta, which is a constant value, logarithm of z1 plus z2 plus z sub p. And then subject to g of x is equal to 0 and h1 of x plus z1 0, h2 of x plus z2 0, and h sub p of x plus z sub p is equal to 0. And all of the z's, z1 to z sub p, are positive value. So this is our barrier function in this case. And this is the barrier parameter. Zeta is our barrier parameter. So ultimately, we want it to be 0. The barrier parameter becomes 0 at the optimum point. So it's not going to be exactly 0, but it converges towards value of 0. So we try to reduce that until it reaches 0. So now, based on this updated formulation, we are going to write the Lagrange function. Before doing that, let me write the compact form for this. What do I mean by compact form? So instead of h1 to hp, we just write it in a vector format. H of x, which shows all of our inequality constraints, plus z is equal to 0, and z's are positive. And the same for the objective function. We just show this in a closed form, I from 1 to p, ln zi. All right. And the barrier parameter is also positive value. So now I'm going to rewrite this formulation in the compact form. So how do we do that? I just write it down as minimizing f of x minus zeta sigma I from 1 to p ln zi, where zetas are positive, subject to g of x, and also z is also here. G of x is equal to 0, our equality constraints. H of x plus z is equal to 0, and z's are positive. So now, what I'm going to do next is to write the Lagrange function for this problem. So our Lagrange function looks like the objective function with the barrier term plus Lagrange multiplier corresponding to the first set of equality constraints. Let's call them lambda. Let's call the corresponding Lagrange multipliers for this mu. Lambda transpose equality constraints plus mu transpose inequality constraints that now are transformed into equality constraint using z. So based on the Lagrange function, we simply write the KKT conditions. So we have derivative of L with respect to x, which is going to be derivative of f of x with respect to x, plus our equality constraint multiplied by lambda, plus our inequality constraint by mu. This is going to be 0 equal to 0. Derivative with respect to lambda, which is nothing but our original equality constraint. Derivative with respect to mu, which is nothing but our transformed inequality constraints that now are equality constraint. And this new term that we have, because here our variables are x's and z's, right? So these are our variables. So z is the new player here, right? So it's going to be mu minus zeta, which is a constant value. Zeta is a constant positive value multiplied by diagonal matrix of 1 over 6 is equal to 0. If I want to like add two more constraints that mu's are positive, because you know mu's are originally referring to inequality constraints, so they have to be zero, positive. And z and these are also positive. So these two are the two constraints that we enforce at each of the iterations. So what's next? Now we are going to formulate Newton-Raphson. Then we formulate Newton-Raphson steps. And based on what we discussed in the previous lectures, we are just going to do for this equality constraint nonlinear problem, right? So that's more convenient to use Newton-Raphson to solve this problem. So let's just look at an example. I'm basically going to write the KKT conditions for this example so that you become familiar with how to extract, how to transform your inequality constraint nonlinear optimization into equality constraint nonlinear optimization, and then write the KKT conditions. Here is our example. Minimizing x1 square plus x2 square, x1, x2, subject to x minus x1 minus x2 plus 4 less than or equal to 0. All right. At the first step, what we are going to do, we are going to define the Lagrange multiplier for this, which is mu. Then interior point method. So we reformulate the problem, minimizing x1 square plus x2 square minus zeta, which is a positive value, logarithm of L and Z. Our variables are x1, x2, and z, subject to minus x1 minus x2 plus 4 plus z is equal to 0. We also know that z should be a positive value. So in the first step, we write the Lagrange function, which is x1 square plus x2 square minus zeta logarithm of z plus mu multiplied by minus x1 minus x2 plus 4 plus z. So now we are going to write the KKT conditions. First, with respect to x1 and x2, x1 is going to be 2x1 minus mu is equal to 0. With respect to x2, 2x2 minus mu is equal to 0. Then with respect to mu, which gives us our transformed inequality constraint, which is now an equality constraint. And finally, with respect to z, this is the new term. So it's mu minus zeta 1 over z is equal to 0. We also have two important constraints. Mu should be greater than or equal to 0, and z should be greater than 0. And then based on this, what we are going to do, we are going to formulate Newton-Raphson to solve this set of equations. So in this lecture, we talked about interior point method. The key idea was to transform an inequality constraint in nonlinear convex optimization into equality constraint. So zeta is a constant term. And then based on this, we rewrite the KKT conditions and solve the optimization problem. So this is the reformulated form with all equality constraints.